Everybody. As I explained in my email, tomorrow was supposed to be Friday Fun Day, but I have to stay home with sick kids. It is less fun, less of a Friday Fun Day to do a video, but it is what it is. And this material is super nice, and we are going to end the semester on a high. Also, as I said in my email, please email me if any of this confuses you or come to class on Monday with questions about this. But the goal of today is to introduce the final models we will study for the semester, the SIR models of disease spread. So that is the point of this video and these slides. I want to introduce to you the classical SIR models, which are used to study the spread of disease. We're going to do 7 things in this video. However, I want to keep the video short and streamlined because nobody wants to watch a 45-minute video. So I will go through this fairly quickly, and some of these things will go quickly because we're not in class. So it looks like a lot, and I guess it is, but it shouldn't take super long. So just a bit of history about the SIR models. They were invented in the 1920s by Kermack and McKendrick, and their paper was the first time that anyone had really tried to systematically, mathematically model disease spread. So this is an image taken from their original paper. This models the outbreak of a disease that takes about 30 weeks to run its course. So the disease peaks around 16 weeks and then dies off by 30 weeks. If we were in class, I would ask you to guess what disease this is. Guessing games are much less fun in this format. But the answer is, this is an outbreak of the plague, a very old-timey disease. So Kermack and McKendrick modeled a plague outbreak. It was on an island off the coast of India, and they drew this is a classic infection curve from the SIR model, and so this is the OG SIR models here. SIR models are designed to model disease spread, but they are not designed to model all diseases. So there are 2 key factors that make a disease SIR modelable. The disease must be contagious via human-to-human contact. So, malaria is like contagious, but it's from mosquitoes to humans. And of course, cancer is not contagious. You have to be able to recover from the disease, is the second key factor. So you have the disease for a relatively short period of time, and then you get immunity once you've recovered. That immunity might not be permanent, but you should at least have a immunity for a while. So, even though HIV is spread via human-to-human contact, HIV is not recoverable in this sense. So SIR models cannot model HIV outbreaks. So here are the diseases we're thinking about: common cold, COVID-19, SARS, etc. There's a long list here. So for such diseases like the flu, like COVID, like anything like that, the population can be divided into 3 groups: those that are currently sick, those that were sick but no longer are, and those that haven't had the disease but could get it. So the SIR model works by building a DE for each of these 3 population groups, which gives you a system of DEs. So you have 3 variables as a system. So in order to get the model up and running, you actually only need to know 3 things: the number of people initially infected, how long the disease lasts in a given individual, so just basically a measure of how long an infection lasts, and then you need to know how contagious the disease is. So you need to have a single number that tells you contagiousness. Some diseases are more contagious than others. Finally, before getting into the models proper, this is a good question here. So if we were in class, when I put the dates 1920s on the screen, some of you may have thought 1920s, that's like 100 years ago. Are these models actually still useful, or are they a historical artifact? And the answer is they are not a historical artifact. They are very much still in use. They're actually surprisingly robust. Now, the models I'm going to show you are the classical SIR models. These models have been adapted and tinkered with over the years. So a lot of the current work in disease spread don't use the straight up classic models, but the models that are used are pretty close. Anyway, so these models are still used. And just as an example, if you put this into Google Scholar, you're going to get more than 18,000 hits over the last 3 years. So this is not just like an academic exercise showing you these models. It's not a historical tidbit or something. You know how textbooks sometimes have those like historical side note or whatever. And sometimes those are interesting, but not particularly useful. This is both interesting and useful. This is not a historical side note. Okay, so also before getting into the models, let's review what math modeling is. I'm going to go through this quickly because we've done it before, but anytime you do a big unit on modeling, you should remind yourself that modeling involves these 4 steps. You have to make assumptions that simplify things. You cannot deal with every variable in reality ever. You state your assumptions, such as, neglecting air resistance if you're a physicist, things like that, and then you can set up a model, an equation or system of equations based on those assumptions. You solve your model, you interpret what gets spit back at you, and we actually will do some of this now. We didn't do this before, like in chapters 2 and 3 or 9, but we're going to do it now, a little bit anyway. Once your model tells you something, you check what it told you against actual data. And if your model spits out numbers that in no way mirror what happened in reality, that means you got to go back here. You got to set up a different model or tinker with your parameters or something. But anyway, in practice, a real math modeler does all 4 of these things. And again, if you check against the data and it comes back suspicious, you got to come back to step 1. Okay, what are the variables of interest in an SIR model? So at any given time, we're interested in the following 3 variables, which were mentioned before. The number of people who have the disease. So the term you'll see in the literature is infected. So you'll see, the number of infecteds is how people will talk about it. But the actual term that people mean is infectious. So even if I have, the flu inside my bloodstream, I might not be contagious right now. I might not be able to infect somebody else. So anyway, when you hear infected, think infectious, capable of spreading the disease. The second variable of interest is the number of people who can no longer be infected. This includes people who are actually recovered and people who have died. So for sort of technical simplifying reasons, we will assume that the population is constant. And if you assume the population is constant, you have to count dead people in your population. So it's a bit of a, misnomer, but when you see recovered in the literature, recovered again means people who have literally recovered and also people who have died. And then also the number of people who could get the disease. That's the third variable of interest. All 3 of those variables depend on time. So the underlying independent variable underneath all of this is time. So when we make graphs later, not in these slides, but on Monday, I guess, the independent variable is time, so there will be a time axis that we'll be graphing against. So we're going to use 2 different sets of these 3 dependent variables. So capital S is the number of susceptible people, S for susceptible. Capital I is the number of infected people at this time, on this day. So like S of 10 is the number of susceptible people on day 10. And then R of T, number of recovered. Now watch this. You ready? S-I-R. SIR models, huh? So that's where that name comes from. Okay, anyway, in practice, sometimes dealing with raw numbers like this is obnoxious. It's easier to deal with proportions. So we'll also use lowercase letters to deal with proportions. So little s of t is like the susceptible percentage, if you like, or proportion of the population that's susceptible. So like little s of 10, that could be a number like 0.3, which is telling you that on the 10th day, 30% of the population is susceptible. Anyway, so, these 2 different sets of variables are related, of course. These are raw numbers, these are percentages or proportions or fractions, whichever term you would like to say. And capital N is the total population. So if you want to move from capital S to lowercase s, you divide by the total population to get a fraction. Now, I wrote these slides for class, so I do have some questions peppered throughout these that I would like you to think about. Now, if we were in class, we would stop down and I would say, hey, these proportion variables, what do they look like over time? So the proportion of the population, that is susceptible to the disease. Over time, as the days move on, what happens to that curve? It's a function of time, so you can graph it against time. And same thing with the recovered population, same thing with the infected population. So if you want to, you can pause the video and think about that, and we'll look at some actual graphs on Monday. So you can sketch these now if you want to or not. So now let's set up the actual assumptions that go into the model so that we can build it. So the first assumption I've mentioned already, we're going to assume the total population is constant. This, of course, is not a literally realistic, accurate assumption. The thing is, though, SIR models are supposed to model things like measles, the flu. These are short-term diseases. So in the short term, you might be okay, disregarding births, disregarding immigration, right? That you disregard those things to have a constant population. If you're going to model HIV, something like that, like a long-term disease, you can't make this assumption. But for us, this might be okay. Okay, second assumption, nobody's added to the susceptible group. That's very much related to assumption 1. You can't create new susceptibles because you don't have births or immigration by assumption 1. So in terms of like a flow, population flow, susceptibles can become infected, can become recovereds, and nothing is inflowing into capital S. Another assumption, the only way that you leave the susceptible group is by becoming infected. So again, these two arrows are all that there is in terms of population flow. That's an assumption of the model. Oh, by the way, some of you might be thinking, well, I mean, you can get from S to R in reality with a vaccine. Like that's what vaccines literally do. They move you from S to R. So I should just say up front, SIR models have a way of incorporating inoculation, but it doesn't involve adding an arrow like this. You just basically start with more people in capital R. Okay, fourth assumption. An infected person stays infected on average for K days, and K depends on the disease you're studying. Some diseases run their course very quickly. So like the flu, an average case of the flu, you're infectious for like 2 or 3 days. I don't know. But for COVID, you can be infectious for like 2 weeks, as we all know. So K varies with the disease. But anyway, what this assumption means is that on a given day, approximately 1 over K's worth of the infected group will recover. So if K equals 4, that means that the disease lasts for about 4 days. So on average, about a quarter of the sick people recover on a given day. Okay, so K again. K is a measure of how long the disease lasts in an individual sick person on average. Finally, we assume that the number of susceptibles depends on 3 things: the number of people already susceptible, the number of infected people, and the amount of contact between them, which makes sense if you think about it. Because capital S of T, think about how that's going to change over time. So like on the, let's say 20th day, so S of 20, what is S going to look like on the 21st day? If you move from the 20th day to the 21st day, what determines that change? Well, if there's a ton of contact between sick people and non-sick people, that's going to drive a lot of change from the 20th to the 21st day. If there's barely any contact, though, there's going to be no change. If there are lots and lots of susceptibles in the population, you might expect S to again change a lot from one day to the next. But if there's not that many susceptible people in the population, you might expect very little change because there's not hardly any susceptibles left. And of course, the more sick people there are running around, the more effect you're going to have on who's susceptible over time. Okay, so let's make this a little more concrete. So most of this is just set up here, by the way. So this tau parameter we're never going to use. It's going to be baked into the model. But I do want to show you where the eventual model parameter comes from. So tau in the literature, tau is like the T, right? It stands for transmissibility. Tau is the probability a susceptible person becomes infected given a contact between this non-sick person and a sick person. So, in other words, if I don't have COVID, but I bump into somebody who has COVID, like maybe I get within 2 feet of them and they cough, I don't know. It's not guaranteed that I get COVID. there's some probability I get COVID and some probability I don't. And of course, that probability depends on if we're wearing masks and all that sort of thing. But anyway, all I'm saying is if a non-sick person who's susceptible comes into contact with a sick person, they don't necessarily become sick. There's some probability they stay susceptible. So suppose that each sick person has an average of C contacts per day with other people in the population. So imagine each sick person is just kind of walking around, bumping into people. The number of bumps they have is C. So the average number of contacts that a sick person will have with susceptibles on a given day is this: number of contacts times the proportion of people who are susceptible. So the question is, on a given day, how many new sick people will be generated by a single sick person on average? Okay, so on a given day, on average, how many new sick people are generated by a single sick person? So to make this concrete, let's put some numbers to everything. So suppose tau is a third. So there's a 1/3 probability that a sick person will make a susceptible person sick when they bump into each other. The sick person bumps into 6 people a day, and the proportion of people who are susceptible today is 50%. So 50% of the population is susceptible to the disease today. Okay, so on that day, an infected person bumps into 6 other people. Because half of the population is susceptible, 3 of those contacts are with susceptibles. So in other words, these 6 contacts, this sick person might be bumping into sick people, might be bumping into recovered people. Those contacts don't matter in terms of disease spread. What matters in terms of disease spread is bumping into susceptible people. So anyway, 6 contacts, half the population is susceptible, so 3 of those contacts are with susceptibles. The transmission probability is a third, so a third times 3 is 1. So on a given day, assuming these 3 numbers, on a given day, each sick person will generate 1 new sick person. As this probability goes up, as this C value goes up, as this proportion goes up, you're going to generate more than 1 new sick person. Okay. So now, the parameter we're actually going to use in the models is this B. It's the probability of transmission times number of contacts per day, which is how I got this 1 right here, right? Eventually. Yeah, C equals 6, yeah. Okay, so each infected individual is expected to generate this many new infecteds on a given day. So the effective contact rate times the number of proportion of susceptibles. That's called the effective contact rate. So all of that to say, there's a parameter called B that's in the model. B, the technical term is called the effective contact rate, but B, the way I think about it, and I think the way most people think about it, it's just a measure of contagiousness. So if your disease is super contagious, then tau is going to be large. And the larger tau is, the larger B is. So it's just a measure of contagiousness. And another way to think about B is this. It's the number of contacts by an infected person per day sufficient to spread the disease. Is how you might think about it. So again, if I cough on you, that's sufficient to spread the disease to you. You might still not get it, but that still counts as like a contact. So in terms of the homework, if you see this, each infected person has 1 contact sufficient to spread the disease every 2 days. That's 1 per 2 for a B value of a half. So you can just form that little fraction. Okay. So anyway, these are all the assumptions we have. So just real quick, population is constant. Nobody becomes susceptible out of nowhere. No births, basically. No immigration. The only way you leave susceptible is to become infected. There's a on average number that measures the length of the infection. There's a B number that measures contagiousness. So that's what we're assuming. So now let's write down some differential equations for these variables we mentioned before. So here is the differential equation for the susceptible population. How is that population changing? Well, note real quick, this is a callback to chapter 2. So if we were in class right now, I'd be scanning your faces to see how pleased you are. Or not pleased, I guess. But you should have some reaction to this. Rate in minus rate out, you know. Now, if we were in class, we would discuss all this, but we're not in class. So let me just say, ds dt. Well, the population S, nothing's coming in, we assumed. So there's only outflow. There's only a rate out. What is that rate out? Well, we said above, and again, I hate to keep flipping back and forth in the slides in the video, but we just said each infected individual, each sick person generates this many new sick people on a given day. So if there are like 10 sick people in the population, you'll have 10 times this, more new sick people on a given day. So here's the number of infecteds. Each one of these gives you this many new infecteds. So every single day, this many people leave the susceptible population. Leave. That's why there's a negative sign. Why is there a negative sign? Because there's only outflow, right? Why is I of t there? Because of this assumption here. Again, this sentence, each infected individual gives you this many new infecteds on a given day. Okay, so once you have this equation set up, you can divide everything in sight by capital N, capital S over capital N. N is the total population. Capital S over capital N is little s. Capital I over capital N is little I. So you have a susceptible equation for the raw number of susceptibles and a susceptible equation for the proportion. Yeah, and again, this is just so classic. Chapter 2 all up in your face again, right? Nice. It's so nice to tie back to that material. Okay, the recovered equation. Let's skip to the recovereds and not think about infecteds yet. Okay, so let's think about this. The proportion of recovereds. So on a given day, what's happening to the recovered population? How is that changing? It's still, by the way, rate in minus rate out. That doesn't change. Rate in minus rate out. Now, if I come back up to this diagram, see, there's only inflow now. Only inflow. Nobody's leaving the recovered group. So back here, it should not be surprising that I have only positive terms here because I only have inflow. Okay, now what's happening here? We said above, and I'm going to quit flipping through the slides because I know it's obnoxious to watch. We said above that on a given day, 1 over k's worth of the infected population recovers. So again, if k were 4, we're saying a quarter of the infected population recovers on a given day. That's how, so 4 is the length of the infection. So if you're sick for 4 days, then on average, a fourth of the infected population becomes well on a given day. So that's all that's happening here. So of the infecteds, 1 over k's worth of them are recovering on a given day. And that's all this is saying. And again, you can go back and forth between raw numbers and proportions if you want to. Raw numbers, here's capital R and capital I. Proportions, little r and little I. Okay. Now, again, if we were in class, we would discuss this in more detail. I'd have you think about it. But the total population is fixed. We're assuming that it's constant. And you're in one of these 3 groups, aren't you? You're either susceptible, infected, or recovered. So the addition of these gives you the total population. Okay. So why do you get something like this? You can differentiate this entire thing if you want to. Put a prime there, prime there, prime there, prime there. Okay, but the derivative of a constant is 0. So ds dt plus di dt plus dr dt is 0. These are capital letters, but you can make them lowercase by dividing by capital N. Okay, so you get this. The 3 derivatives combined add up to 0, and we get that from the fact that the total population is fixed. Okay, now you can explain why this equation is true. So di dt, what is that? That's dr dt minus ds dt. So you can get it that way. Also, though, again, rate in minus rate out. This is the chunk of people who are leaving the susceptible population. So there used to be a negative right here for the outflow from susceptibles, but where are they going? They're going to infecteds. So again, this is the outflow from susceptible, which becomes inflow for recovered. And this is without the negative. So think about it without the negative. That's what we just had here, right here. These are people flowing into the recovered population. Where are they flowing from? From the infecteds. So rate in minus rate out. Okay, so that rate in minus rate out comes up 3 times actually. So in terms of a model, we have a system of 3 differential equations. We have 3 variables, S, I, and R, all of which depend on time. So instead of SIR, we could have X1, X2, X3, if you like, or XYZ, depending on time. And B and K are constants that depend on the particular disease and how the population behaves. So once I give you a specific disease, like the flu, like COVID-19, those diseases have particular B and K values associated with them that you could plug in. In order to solve a model like this, to get a specific solution, we need not just differential equations, we need initial value problems. Okay, so I can't just give this to you and say, solve this, tell me what the populations do, because there's no initial conditions. So in the classical SIR model, we're going to assume that initially, almost the entire population is susceptible. And initially, there's just a tiny amount of people who are sick. So initially, there's like that one tourist who flew to New York City from Italy, who was sick. So at the beginning of COVID, there was initially just like 1 sick person in New York City, or maybe like 5 sick people in New York City. So basically nobody. Not literally nobody. That's not an equal sign, approximately. And basically nobody has recovered. So in terms of proportions, again, at the beginning of the outbreak, approximately everybody, proportion of 1, is susceptible. Approximately nobody is sick, but again, not 0. So there's some tiny proportion of people who are sick, and then nobody is recovered yet. So again, those of you who think about vaccination might be saying, that's not how things work for some diseases. Like with measles outbreaks, a bunch of people are recovered because measles vaccines exist. So again, my response to that is we will get to vaccines later. In this classical setup, you're not worrying about vaccines yet. You're basically assuming when the disease comes on the scene, nobody has prior immunity to it. So here, in all of its glory, is an SIR model. And I'm giving you the proportion version. There's a susceptible equation with some initial susceptible population or proportion. So this would be about 1 for us. Infected equation with some initial proportion of infected people and a recovered equation. Where again, for a specific disease in a specific context, B is a number filled in. S naught, I naught are numbers filled in. So the variables are S, I, and R. And what we would like to do is get graphs for them. So, somehow figure out what S, I, and R are doing over time. And if you want the SIR model with the raw numbers, you can start to see why people don't deal with the raw numbers as much. I mean, look at these fractions. It's obnoxious, dividing by capital N. So this is nicer on the eyes here with proportions. But if you like, this is now the raw number version where S is the raw number of people who are susceptible and so on. Same model, just all the letters are capitalized and you have to divide by capital N. Okay, so the way I want to conclude this video and how we would have concluded class is by thinking about this. There are 5 numbers to fill in a classical SIR model. B, K, S of 0, I of 0, R of 0. So again, coming back here, for a specific disease, this would be filled in as a number. This would be filled in as a number. You can't really solve the systems unless you do that. This is also a number, and so on. So there are these 5 numbers to fill in for a specific disease. Which of these 5 could we actually try to control at all? Do we have any control over any of these 5 numbers? And again, if we were in class, I'm sure you all would tell me the correct answers. But since we're not, and we're keeping things quick, we're trying to keep them quick, K, you can't really control that. That was the length of the disease. I mean, it's possible you could create drugs. Like, I guess with the flu, we have drugs that can shorten the infectiousness period a little bit. But generally speaking, no. You can't, like, just in general, you can't take a COVID patient and try to shorten their duration of the disease in any significant population level way, you know. So K is an average. So maybe for a specific patient, you can shorten their infectiousness period, but in general, no, you're not doing that. You can't really control the initial number of infecteds, assuming that there are some. I mean, you could like wall off your city, I guess, and keep I of 0 at literally 0, but generally speaking, no. Once infected show up, you don't really have much control over I of 0. You do, however, have control over other things. So little r of 0. If you can make a vaccine and you can get people to use it, which is not a trivial task nowadays, right? But if a vaccine exists and people use it, the effect will be that R of 0, so the initial proportion of recovered people, will be high. And if R of 0 is high, then the initial proportion of susceptibles will be low. And this can help stop outbreaks from occurring. So this is like how measles outbreaks were stopped for so many years. R of 0 is very high. There's just not that many people susceptible to measles anymore if you have a vaccine and people use it. So you can control R of 0 assuming you have a vaccine. B was a measure of contagiousness. So you can make B small if you want to, and depending on how draconian you want to be, you can make B 0 or close to 0. So as I'm making this video in like Shanghai, China, they are like the government is literally locking people in their houses. If you do that, you can make B pretty small, you know. So I'm not saying you should do that, but I'm saying there is some control you can exert over B. But, you know, quarantining people, social distancing, if you can get everybody to wash their hands all the time, measures like this can make B lower because it will make the disease less contagious. Mask wearing, of course, things like that. So again, I don't want to wade at all into the politics of that sort of thing. I'm just saying, like, purely from a mathematical standpoint, right? If somebody says, hey, can you make B small? The answer is yes, you could. Maybe you shouldn't. Again, I am not advocating what the Chinese government is doing to citizens of Shanghai, you know. Anyway, okay, so that's an introduction to the SIR models. Now, notice today, we did no solving of this. We didn't even fill in any of these numbers for a specific disease. So next time what I want to do is pick a specific disease so that we can fill in B and K, and then we can solve this system and get graphs and things like that to really analyze what this kind of system predicts about how diseases behave. Because again, why would you build a model? What is the point of modeling? The answer is to make predictions, and we made no predictions in this video. So next time, we'll build a specific model with specific B and K and make predictions. Okay, so that's it for this video. If you have any questions, please feel free to shoot me an email. Otherwise, I'll see you on Monday.